Imagine a world without computers, smartphones, or the internet. It seems unfathomable today. Yet, this was our reality just a few decades ago. The invention that revolutionized our world and ushered in the information age is the transistor. And at the heart of this revolution lies a tiny semiconductor device called the MOSFET. MOSFET stands for Metal-Oxide-Semiconductor Field Effect Transistor. It is a type of transistor that uses an electric field to control the flow of current. This simple yet ingenious device acts as an electronic gate, switching on and off billions of times per second, enabling the processing and storage of information in digital circuits. The importance of MOSFETs cannot be overstated. They are the fundamental building blocks of modern electronics found in virtually every electronic device imaginable. From the smallest microchips to the largest supercomputers, MOSFETs are the unsung heroes that power our digital lives. Their small size, low power consumption, and high switching speed make them ideal for a wide range of applications. Without MOSFETs, our world would be a vastly different place. The story of the MOSFET begins in the early 20th century with the development of quantum mechanics. Physicists began to unravel the mysteries of the atom, discovering the existence of electrons and their behavior in materials. This newfound understanding paved the way for the invention of the transistor in 1947. The first transistor, known as the point contact transistor, was a bulky and unreliable device. However, it demonstrated the principle of using a semiconductor material to amplify and switch electronic signals. Scientists continued to refine the transistor design, leading to the development of the bipolar junction transistor, or BJT, in the 1950s. While BJTs offered improved performance over their predecessors, they still suffered from limitations. They consumed a relatively large amount of power and were not easily miniaturized. The search for a better transistor led to the invention of the MOSFET in 1959 by Muhammad Atallah and Dawon Kong at Bell Labs. The MOSFET offered several advantages over BJTs. It had a simpler structure, consumed less power, and was more amenable to miniaturization. These characteristics made it the ideal candidate for use in integrated circuits, which were becoming increasingly complex. To understand how a MOSFET works, it's essential to first grasp its basic structure. Imagine a thin layer of silicon, a semiconductor material, acting as the foundation. This silicon substrate is typically doped with impurities to create regions with an excess of either electrons known as N-type or holes known as P-type. On top of the silicon substrate lies a thin insulating layer, usually made of silicon dioxide. This layer acts as a barrier, preventing current from flowing between the gate and the substrate. Above the insulating layer sits the gate electrode, typically made of a metal such as aluminum or polysilicon. On either side of the gate, within the silicon substrate, lie two heavily doped regions called the source and the drain. These regions are responsible for injecting and collecting the charge carriers that flow through the transistor. The region between the source and drain, directly beneath the gate, is called the channel. This simple yet elegant structure forms the basis of the MOSFET. By applying a voltage to the gate, we can control the conductivity of the channel, thereby regulating the flow of current between the source and drain. The fabrication of a MOSFET is a complex and intricate process involving hundreds of steps performed in a highly controlled environment. It all begins with a wafer of pure silicon, sliced thinly from a single crystal. This wafer undergoes a series of cleaning, oxidation, and photolithography steps to create the desired patterns on its surface. Photolithography is a crucial step in the fabrication process. It involves using ultraviolet light and a photosensitive material called photoresist to transfer a circuit pattern onto the wafer. The exposed photoresist is then developed, revealing the areas where the underlying material will be etched away or doped with impurities. Ion implantation is another critical step, used to introduce dopant atoms into the silicon lattice. These dopants alter the electrical properties of the silicon, creating the N-type and P-type regions necessary for transistor operation. Multiple layers of materials are deposited and patterned using various techniques, including chemical vapor deposition and sputtering. Finally, metal contacts are formed, connecting the transistor to the external circuitry. The completed wafer is then diced into individual chips, each containing millions or even billions of transistors. These chips are packaged and tested rigorously before being integrated into electronic devices. Section 5. The dance of electrons. How MOSFETs orchestrate current flow. Now let's delve into the fascinating world of how a MOSFET actually works. Imagine the gate as a dam, controlling the flow of water, electrons, between the source and drain, which act as the upstream and downstream reservoirs respectively. When no voltage is applied to the gate, the channel remains closed, acting like a barrier to the flow of electrons. The MOSFET is in its off state, and no current flows between the source and drain. However, when a positive voltage is applied to the gate, it attracts electrons from the P-type substrate towards the gate. These electrons accumulate near the silicon insulator interface, forming a thin, conductive channel between the source and drain. This channel allows electrons to flow freely from the source to the drain, turning the MOSFET on and allowing current to flow. The amount of current flowing through the channel is proportional to the gate voltage. A higher gate voltage creates a wider and more conductive channel, allowing more current to flow. Conversely, a lower gate voltage reduces the channel width, restricting current flow. This ability to control current flow with a voltage signal makes the MOSFET an incredibly versatile and efficient electronic switch. Section 6. MOSFETs in action, a tapestry of applications. The applications of MOSFETs are vast and diverse, permeating every aspect of our modern lives. They are the workhorses of the digital world, found in countless electronic devices from smartphones and computers to cars and airplanes. In computers and smartphones, MOSFETs form the heart of microprocessors, memory chips, and other integrated circuits. They process and store information at lightning-fast speeds, enabling us to browse the internet, play games, and run complex software. In consumer electronics, MOSFETs are found in televisions, cameras, and gaming consoles, providing high-quality displays, efficient power management, and seamless audio and video processing. They are also used in automotive electronics, controlling engine timing, braking systems, and other critical functions. In the medical field, MOSFETs are used in pacemakers, hearing aids, and other medical devices, improving the quality of life for millions of people. They are also used in scientific instruments, telecommunications equipment, and industrial control systems. The list goes on and on. MOSFETs have revolutionized our world, and their impact continues to grow with each passing day. Section 7. Miniaturization and beyond, the shrinking world of MOSFETs. Since their invention, MOSFETs have been on a relentless march towards miniaturization. Gordon Moore's famous prediction, known as Moore's Law, stated that the number of transistors on a chip would double approximately every 2 years. This prediction has held true for over 5 decades, driven by advances in MOSFET technology. As MOSFETs shrink in size, they become faster, consume less power, and cost less to manufacture. This has led to an exponential increase in computing power and a dramatic decrease in the cost of electronics. Today's smartphones are more powerful than the supercomputers of just a few decades ago, thanks in large part to the miniaturization of MOSFETs. However, as we approach the limits of traditional silicon-based MOSFET technology, researchers are exploring new materials and architectures to continue this trend of miniaturization. FinFETs, nanowire transistors, and other novel designs are being developed to overcome the limitations of planar MOSFETs and extend Moore's Law into the future. Section 8. Powering the future. MOSFETs in energy-efficient electronics. As our reliance on electronic devices continues to grow, so too does our demand for energy. MOSFETs, with their low power consumption, play a crucial role in developing energy-efficient electronics. From low-power processors in smartphones to energy-efficient power supplies in data centers, MOSFETs are helping to reduce our energy footprint and combat climate change. They are also enabling the development of new energy technologies, such as electric vehicles and renewable energy systems. Wide bandgap semiconductors such as silicon carbide and gallium nitride are being explored for use in high-power MOSFETs. These materials offer higher breakdown voltages and lower on resistances, enabling more efficient power conversion and reduced energy losses. MOSFET-based power electronics are also playing a vital role in the development of smart grids, which are more efficient and reliable than traditional power grids. By enabling the integration of renewable energy sources and improving the efficiency of power distribution, MOSFETs are contributing to a more sustainable energy future. Section 9. Conclusion. The enduring legacy of MOSFET technology. The invention of the MOSFET was a watershed moment in human history, ushering in the information age and transforming our world in countless ways. From the smallest microchips to the largest supercomputers, MOSFETs are the fundamental building blocks of modern electronics. As we continue to push the boundaries of technology, MOSFETs will undoubtedly play a pivotal role in shaping our future. From artificial intelligence and machine learning to quantum computing and beyond, the possibilities are limitless. The relentless march of MOSFET miniaturization, coupled with the development of new materials and architectures, promises to bring even more powerful and energy-efficient electronics in the years to come. The enduring legacy of MOSFET technology is a testament to human ingenuity and our insatiable thirst for progress.